In the last few lectures, we were discussing optimality conditions for constraint optimization problems. Especially, we got to know the KKT optimality conditions. Now, slowly, we are moving towards discussing methods to solve constraint optimization problems. But before that, in this lecture, we are going to start a new unit of the course, Unit 7, on the topic of the Lagrange duality theory. We shall find that corresponding to a given constraint minimization problem, there is a hidden maximization problem which plays a role behind to solve the constraint minimization problem. This hidden maximization problem for a given minimization problem is called the dual problem. We shall formulate this dual problem with the help of the Lagrangian function and thereby calling this dual problem as the Lagrange dual problem for the given constraint minimization problem. We shall find that irrespective of whether or not the given constraint optimization problem is a convex optimization problem, the Lagrange dual problem must be a convex optimization problem, and therefore it might be easy to solve the Lagrange dual problem. And by solving the Lagrange dual problem, sometimes we will be getting a solution to the original problem. And therefore, if it is easy to solve the dual problem, we go for solving this dual problem, and thereby we shall be getting a solution of the given original optimization problem. So in this lecture, we are going to discuss thoroughly the topic of the Lagrange duality theory for constraint optimization problem. Let's start. Neatly, the topics of discussion in this lecture are as follows. At first, we shall formulate the Lagrange dual problem, and then we will figure out a geometrical interpretation of this Lagrange dual problem. We shall also get to know how does one discover the duality theory. Afterwards, we will get into knowing a few results of the dual problem. The Lagrange dual problem for any given nonlinear problem is a convex optimization problem. After knowing this fascinating result that the Lagrangian dual problem is a convex optimization problem, we shall go with some more analysis on the Lagrange dual function. We will find that some weak duality result happens to be true, which says that for any given pair of primal and dual feasible points, the value of the dual objective function is always less than or equal to the value of the primal objective function, and hence it is called as the weak duality result. The value of the objective function of the dual is always weaker than the primal objective function value. After knowing this weak duality result, we shall immediately know a few corollaries, where we will find that if you have obtained a pair of feasible points of the primal and the dual, where the primal and the dual objective function values are identical, then that pair of feasible points of the primal and dual will give us respectively the optimum value of the primal objective function and the optimum value of the dual objective function. When these primal and the dual objective function values are identical, in that case we will say that strong duality has happened. And towards the end of this lecture, we will find certain conditions satisfying which this strong duality is going to hold. So now let's start our discussion with the formulation of the Lagrangian dual problem for a given nonlinear optimization problem. We start with considering the following nonlinear programming problem, where as usual we take a constraint optimization problem to minimize a function of several variables subject to gix is less than equal to 0 or I is equal to 1 to till m, and hjx is equal to 0 for j is equal to 1 to till l, and small x is belonging to a set capital X, a non-empty subset of the n-dimensional Euclidean space Rn. This is your given nonlinear programming problem. For this nonlinear programming problem, we formulate the dual problem, the Lagrange dual problem, as follows. We define the Lagrangian of this nonlinear programming problem as a function defined on the set Rn cross Rl, a real valued function, which is defined by, as usual, that the Lagrangian function L x lambda mu is equal to fx plus, in lambda we have m many components. This summation then goes with lambda I g I x, I is from 1 to m, plus summation j is equal to 1 to L mu j hjx. This Lagrangian function is defined for every given small x in capital X. So here, instead of Rn, you may consider capital X. We notice that this Lagrangian function capital L can also be written in a compact manner in the vectorial form as follows: that if I consider a vector valued function g from Rn to Rm, where the ith component of this function g is gi over here. That means you are considering the function gx is equal to having the components g1x, g2x till gmx. Similarly, consider in a vectorial form these equality constraints to be written as hx, where the jth component of h is hj. So here this hx is given by the first component h1x, the second component h2x, and the last component is hlx. Considering these g and h, we notice that this Lagrangian function L can be written in the vectorial form as fx plus lambda transpose gx plus mu transpose hx. After defining this Lagrangian function, we formulate the dual of the given nonlinear programming problem P. Is the problem as follows. It is a maximization problem. Maximization of the function theta lambda mu subject to lambda greater than or equals to 0 and mu is belonging to RL, where this function theta, the objective function, which we call as the objective function of the dual problem, is given by theta lambda mu is equal to, for a given value of theta and mu, you go for considering this function L and you take the minimum most value, or in terms of more erudite fashion, you consider the infimum value of this Lx lambda mu for a given value of lambda and mu. The value that you will get as the infimum value of this function L over the set capital X is the value of the function theta. So we consider this theta lambda mu to be defined as infimum of Lx lambda mu, infimum over the set capital X. Here you notice that these lambda and mu, they are vectors. These vectors, lambda has components, these m many components, lambda 1, lambda 2 till lambda m. Mu has components mu 1, mu 2 till mu l. And these variables, these lambda i's, mu j's, they are called the variable of the dual problem, or the dual variables of the given problem P. Let us name this problem as say D, and mention here that the variables of this problem D are called as the dual variables. Now here we notice that while defining this objective function of the dual problem, we have considered the infimum to be taken of the Lagrangian function over the set capital X. And you notice that this set capital X in the primal problem, it is a subset of Rn, a general subset. Commonly in capital X, we keep those restrictions like the bounds of the variables. That is, capital X is commonly a box constraint, like the product of the intervals a1, b1, a2, b2 till, let's suppose we have n many variables till an, bn, where this a1, b1, this closed bounded interval is the range of the values for x1 A2, B2 is the range of values for x2, A and B, and this interval is range of values for the nth component of the variable x, and capital X is then described in terms of the Cartesian product of all these intervals. As geometrically this set capital X gives us a kind of rectangular parallelepiped or a box kind of thing. We commonly refer the set capital X as box constraint, and in general this capital X is certain abstract set for which we face difficulty to mathematize them in terms of certain constant functions or so, or simply also we consider this box constraint, or simply sometimes we just go with taking this capital X as the entire n-dimensional Euclidean space. So in general this capital X is just an abstract set, but here you notice that in capital X we can even include some of the restrictions over here. Like in capital X, let's suppose we are including in capital X the first restriction g1x less than equal to 0, and let's suppose we are also including some of the equality constraints. Let's suppose h1x is equal to 0 and h2x is equal to 0 are also included inside the set capital X, and accordingly this problem, primal problem P, can be recasted as minimization of fx subject to you have small x belonging to capital X dash, say, where in capital X dash we keep those points such that we have g1x less than equal to 0, together with, let us include one or two constraints in the equalities. H1x is equal to 0, H2x is also equal to 0. Let us define x dash as this set. Then we go for taking the problem capital P equivalently in terms of minimization of fx subject to g2x, g3x till gmx, those are less than equal to 0. And here in the equality constraints, as you have included the first two constraints inside the set capital X dash, go for taking the rest of the equality constraints here, h3x till hlx is equal to 0. Then we see that this problem and this problem, they are equivalent. Now for this problem, if we go for formulating the Lagrangian, then we see that in the Lagrangian you will have here this summation to be revised from I is equal to 2 to m, and this summation has to be revised from j is equal to 3 to l. So we get a new Lagrangian function, and accordingly we notice that with the new Lagrangian function, if we go for taking the infimum of the new Lagrangian function over the set x dash, we will get a new dual function theta dash c, and then we will find that this dual problem is completely revised than that of this dual problem when we treat the abstract set capital X to be revised as the set x dash. And therefore for a given primal problem, for this nonlinear programming problem, we can have several Lagrangian dual problem. Therefore the Lagrangian dual optimization problem is not a unique optimization problem corresponding to a given primal problem. But with respect to a given fixed capital X, we notice that this Lagrangian dual problem is a unique problem given by the problem formulation as over here. So I write over here neatly that as there are many ways of defining capital X versus the constraints Z and H, there are many possible Lagrangian duals for the given optimization problem P. This abbreviation capital P for the given problem is for the term primal. You know, this word primal for this dual problem was due to Tobias Danzig. Tobias Danzig was father of George Danzig, the father of linear programming problem. The term dual came in the following manner. It was actually evolved in the context of a linear programming problem. One day around 1954, W. Urquhart Hay, who was responsible for the first commercial grade LP software, one person in R&D Corporation, USA, he requested George Danzig to meet him once,
And then in the conversation of Orchard Hay and George Danzig, Orchard Hay requested George Danzig to give a word that stands for the original problem, this problem P, of which this D, is the dual. George Danzig in turn asked his father, Tobias Danzig, and Tobias Danzig is well known for his books for popularizing the history of mathematics. George Danzig requested Tobias Danzig, his father, to give a name for this problem P, this original problem P, for which this is the dual, the D problem. Although Tobias Danzig never took an interest on linear programming problem of George Danzig, but on this occasion, that when George Danzig requested so many times to his father that you please give a name for this problem P, then Tobias Danzig did give the matter some thought and several days later suggested the word primal as the natural antonym for the problem dual. Since both primal and the dual, these two terms are derived from the Latin origin, and it was Tobias Danzig who gave this name primal for this problem, for this original problem with which we have started, for which this problem D is the dual. So in our discussion, we will refer then this original problem as the primal problem, this problem as the dual problem. Now let me describe a geometrical interpretation of this dual problem. For identifying a geometrical interpretation of the dual problem, let me go with the simpler case that I consider the primal problem as a problem with just having only one inequality constant, and let me describe for that particular problem the geometrical interpretation, and from the geometrical interpretation for that particular problem we will be able to identify a geometrical interpretation for a general problem P. So for the geometrical interpretation, I consider the primal problem as minimization of the function of several variables fx subject to, let us suppose we only have one constraint, say gx less than equal to 0. And here we also have the restriction that x is belonging to capital X, the abstract set. Corresponding to this primal problem, we notice that the dual problem is given by maximization of the function theta lambda over lambda greater than equals to 0, where this theta lambda, the dual function, is given by infimum over capital X of the Lagrangian function Lx lambda, which in turn we notice that infimum over capital X of the function fx plus lambda gx, right? Now to find a geometrical interpretation of this dual problem, we notice the following, that you consider to take, let's suppose a new variable y as your gx and z as your fx. You consider these two new variables where small x belonging to capital X. Now consider a set, say capital G, which is the set of all points yz, where y is equal to gx, z is equal to fx, small x belonging to capital X. We notice that geometrically this set capital G identifies a region given by as follows, that let's suppose this is our abstract set capital X from where the points small x's are taken. Maybe let's suppose we are having three variable problem, and then in a three-dimensional space, let's suppose the set capital X is over here. You could have taken any number of variables. Let me just geometrically, let's suppose I take here capital X is your this set. Now corresponding to every given point small x inside this set capital X, we notice that we will get a point in the set G, this capital G, and capital G is a set in the plane of yz. Let's suppose corresponding to a chosen small x, we get by this map, the map this gf, by this gf map we get a point over here, say. Now we vary this small x in the set capital X, and accordingly the collection of points as the image of this function gf will give us a region, say, of this type. This region, let's suppose, is the image of the function gf of the set capital X. So let's suppose this is our set. That set is the set capital G, right, which is obtained as the image of the set capital X under this mapping, whose first component is G and the second component is this F. Now in this set capital G, let us try to look at the primal problem. We see that with this reformulation of the variables, the primal problem is equivalent to minimization of the function fx. Fx is now redefined as z. So minimization of z subject to gx less than equal to 0 is nothing but y is less than equal to 0, and small x belonging to capital X essentially gives us that yz is belonging to the set capital G, right? So in terms of the new variables z and y, we notice that the primal problem is given by this particular problem. And we see that when this yz is belonging to capital G, we are inside of this set. Now we are to find the minimum most value of z inside the set capital G when this small y is less than equal to 0. That means the feasible region for this primal problem is this part, the left hand side part of this set G. By left hand side I mean the side in which we have y less than equals to 0. So this green shaded region is the feasible set of this primal problem, right? Now inside this feasible set, the minimum most value of z in this figure, we notice that is given by at this point, at which we notice that we have the minimum most value of z inside this green shaded region. So geometrically we see here that this point is our primal optimum value. Now let us look at the dual problem. We notice that the dual objective function value theta lambda for a given value of lambda in terms of this yz is given by theta lambda is equal to infimum most value of the function z plus lambda y, where this small x belonging to capital X is equivalent of this yz is belonging to this set capital G, right? So I write here infimum over the set capital G. So for a given value of lambda, the infimum most value of this function over the set capital G gives us the function value of theta. Now to find an infimum most value of this expression, we see that this expression z plus lambda y has level sets. Let's suppose corresponding to the alpha level set of this function is obviously a straight line in the yz plane. For a given value of lambda, we notice that this expression identifies a line in the yz plane, right? And this line has slope minus lambda. So let's suppose this line is the line z plus lambda y is equal to alpha. For a given alpha value, let's suppose this is your line z plus lambda y is equal to alpha. Now to find the value of theta lambda for a given lambda, once you have fixed the value of lambda, obviously the slope of this line is fixed, right? Now to find an infimum most value of this expression, now we go for altering this level value alpha. As we need to find the infimum most value of this expression inside this set capital G, we go for dragging this line until this line is about to leave the set capital G, and at the extreme situation we will see that this line, which is a line parallel to this z plus lambda y is equal to alpha, is going to give us the infimum most value of this expression z plus lambda y inside the set capital G. And this extreme situation of this line for which this infimum value is attained is certainly the situation where this line is about to leave capital G and touching the set capital G, and the set capital G entirely lies in one half space of this particular line. Such a line which touches the set, and in one half space of that line the entire set is lying, is called a supporting hyperplane or a supporting line. As if this entire set G is supported below by this line. Once a line parallel to this line is going to support the set capital G, that line, the supporting line, is going to give us the infimum most value of the expression z plus lambda y. And corresponding to that supporting line, the value of alpha, that is your z plus lambda y, is equal to, let's suppose, alpha bar. This alpha bar is giving us the value of this theta lambda, right? So corresponding to a given lambda, you go for identifying the slope as minus lambda. Accordingly, you consider the parallel lines having slope minus lambda, and out of these parallel lines, the line that supports the set capital G is going to give us the infimum most value of the function z plus lambda y, and hence this alpha bar is the value of this function theta lambda. And here you notice that this alpha bar is nothing but the z-intercept of this line. Z plus lambda y is equal to alpha bar, and therefore the value of this alpha bar is this much amount of value, the z-intercept of this supporting line. So we observe here that this much amount of value, the z-intercept of this line, gives us the value of theta lambda corresponding to the chosen lambda, for which minus lambda is the slope of all these parallel lines. Now, by varying the value of lambda, let's suppose, to some other value, let me consider some other value. Let's suppose I take off the value of lambda for which minus lambda is the slope of this line, say, and for this supporting line we notice that the value of the z-intercept of this supporting line is this much amount. So theta lambda values are these z-intercept of all these supporting lines to the set capital G. The dual problem is essentially asking us to find maximum most value of all these z-intercepts of these supporting lines to the set capital G. So you keep varying the slope of all these lines, this blue line or this magenta line, and so on. Accordingly, you go for identifying the z-intercept of all those supporting lines. The maximum most value of all these z-intercepts of the supporting line will give us the solution to this dual problem, right? And therefore, the dual problem is essentially equivalent of finding the slope minus lambda of all these supporting lines, or in the higher dimension supporting hyperplanes, such that those intercepts on the z axis is maximal. So find the slope this minus lambda of the supporting hyperplanes of the set capital G, such that its intercept on the z axis is maximal. So this is your the geometrical interpretation of the dual problem. And for the primal problem, the geometrical interpretation is that you find the minimum most z value of all the coordinates yz's, those are lying inside this green shaded region. And therefore this particular point, this red point, is going to give us the primal optimum point. And for the dual problem, the optimum value, the maximum value of all these z-intercepts of the supporting hyperplanes can be identified by these supporting hyperplane to the set capital G. And therefore this much amount of z-intercept, this much length, is going to give us the dual optimum value. We see that for the primal optimum point, the value of z, and for the dual optimum value, the value of the z-intercept, they are identical for this particular figure that I have drawn for the set capital G. But this might be not always the case, that the primal optimum value is identical to the dual optimum value. For instance, let's suppose if I go for taking out the region for this capital G as a set, let's suppose, of the following type. Let's suppose I take the feasible region is, let's suppose, of this kind. Let's suppose this is our the set capital G in the YZ plane. For this set, we notice that the primal problem will identify the minimum most value of Z where the YZ point is lying on this green shaded region, because in the feasible region of the primal problem we have the points yz belonging to capital G, but y has to be less than equal to 0. That identifies the primal feasible region as this green shaded region. Now inside this green shaded region, the minimum most value of z is obtained over here, and that identifies the value of z is this much amount. So this much amount gives us the primal optimum value. But for the dual problem, we notice that this supporting hyperplane is going to give us the optimum value of the dual problem. And for this supporting hyperplane, for this supporting line to the set capital G, we see that the value of z-intercept of this supporting hyperplane is this much, which is your dual optimum value. So for this figure of capital G, we see that at the optimum situation, the primal optimum value and the dual optimum value are not identical. If the lower part of this region of this capital G is a convex region, then we can easily see that these primal and dual optimum values are identical, and that is what exactly happening over here. Inside this set capital G, we notice that this lower part is a convex kind of part, right? And once this lower part is a part of the surface of a convex function, then we see that obviously the primal and the dual optimum values are going to be identical. But for a non-convex part, like if the lower part is the surface of a non-convex function, then we see that there must be a gap between the primal and the dual objective function values. This gap, this much amount of gap, the difference between the primal and the dual objective function value, is known as the duality gap. So for a non-convex optimization problem, that means when the primal problem is a problem where the objective function and constraints, they are not convex functions, then in that case it is expected that there is a duality gap. But in the case when this function, the objective function, is convex, the constraints, the inequality constraints are given by convex functions, the equality constraints are affine functions, then certainly the feasible region for the problem is a convex set, and thereby we will be getting the set capital G, a convex set. And for a convex primal problem, this duality gap is going to be equals to 0, but for a non-convex problem, a positive value of the duality gap is expected. So for a convex optimization problem, then we can just go for solving the dual problem and you will get the solution to the primal problem, right? So it might be attractive that for the convex optimization problem, if the primal problem is difficult to solve, you can just go for solving the dual problem if that is easy and obtain an optimum solution to the primal. This is very interesting, right? However, for a non-convex problem, we may not have an optimum solution by solving the dual problem. We may not have an optimum solution to the primal problem because there will be a duality gap expected. Although for a non-convex problem, the dual optimum value is not going to give us an optimum solution to the primal problem, but the dual optimum value is certainly a lower bound of the primal objective function that we shall see later on. And once you have obtained a lower bound for the primal objective function, then with that lower bound you can start your optimization algorithm, and that lower bound can give us a warm initial point to start your optimization algorithm for constrained optimization problem. So even if the problem is not a convex problem, even if the dual optimum value is not going to give us an optimum solution to the primal, but by solving the dual problem, you are getting a warm initial point to start with your optimization algorithm to solve your primal optimization problem. So solving the dual problem is not going into vain. It is really fruitful when the problem is a convex problem. By solving the dual problem, you will be able to obtain an optimum solution to the primal problem. And when the problem is not convex, by solving the dual problem, you are going to get a warm initial point to start with your optimization algorithm to solve the primal problem. Now we shall get into some results for this duality theory, like this dual optimum value is a lower bound of the primal objective function, and so many other facts like theta is a convex function and so. But before that, let me inform you some perspective of how one has gotten this idea of framing the dual problem as this one, and from that dual problem you are going to solve the primal problem if the problem is a convex optimization problem. So let me inform you some perspective from where you will find that how one has discovered this duality theory, the formation of this dual problem. There are a few perspectives how one has discovered this duality theory. Let me inform you the following perspectives. The common perspective are three. Those are the min-max perspective, the penalty perspective, and the 2% zero-sum perspective. So let me describe this perspective on how one has discovered, how one has got this idea of framing the dual problem. The first perspective that I would like to inform is the min-max perspective. In the min-max perspective, we notice that we can rediscover the primal objective function from the Lagrangian function. It is as follows. We notice that the maximum most value of Lx lambda mu of the Lagrangian function corresponding to a given value of x. Let us denote by x bar. Maximum most value of this Lagrangian function over lambda greater than equals to 0 and mu unrestricted is given by as follows. As the expression of L x bar lambda mu is given by f x bar plus lambda transpose g x bar plus mu transpose h x bar. Then notice that if the point x bar is a feasible point, that means if x bar satisfies all the constraints g I x s are less than equal to 0, the point x bar is lying inside the set capital X, and the point x bar satisfies all the equality constraints h j x is equal to 0, then we notice that when x bar is a feasible point, then the maximum most value of this L x bar lambda mu is nothing but f x bar. This is due to the fact that this entire expression is certainly less than equals to f x bar, because g x bar has all components less than equal to 0 and the components of lambdas are all non-negative. Therefore, this portion lambda transpose g x bar is certainly less than equal to 0, and this portion is equal to 0 when x bar is a feasible point, and therefore this entire encircled portion is less than equals to fx bar. For the choice of lambda is equal to 0, we see that this encircled expression is exactly equals to fx bar, and therefore the maximum most possible value of Lx bar lambda mu is the value fx bar. And when the point x bar is not a feasible point, then we see that if x bar is not feasible, then at least one of the constraints is violated, that out of the components of gx bar, at least one component is there for which you have positive value, or at least you have one component here in this hx bar which is non-zero. Now you choose that particular component of g for which gx bar is positive, or that particular component of h for which hx bar is not equals to 0. Then we see that by taking off a component for which, let's suppose, gix bar is greater than 0, the ith constant is violated. Then you look at the associated lambda I, you take off a big and bigger value of this lambda I, and accordingly you will find that this term lambda I times gi inside this expression can be blown up, and ultimately you will find that if one of the components in gx bar is greater than 0, or one of the components in hx bar is not equals to 0, then this value of Lx bar lambda mu can be blown off, and it will reach to positive infinity when the point x bar is not a feasible point. So in the feasible set, we see that the function f, the objective function of the primal problem, is rediscovered by taking off the maximum most value of Lx lambda mu. That is, we see that fx is nothing but the maximum of Lx lambda mu over lambda greater than equals to 0. And therefore the primal problem can be stated as minimization of this fx over x being feasible, and therefore that is your minimum most value of maximum of this function over the set capital X. That is, the primal problem is equivalent of minimizing this function maximum over lambda greater than equals to 0 of the Lagrangian function, and this minimization has to be taken over the feasible set, where this capital F is the feasible set of the primal problem. So the primal problem is precisely this min-max problem. Once a problem can be recasted as a min-max problem, it is really tempting that you go for interchanging this minimum and maximum operation, and then go for solving either of the problems, that min-max or max-min, whichsoever is easier, and accordingly you may expect that you have solved the problem, this min-max problem. So here I just write out here that the question, that is it not tempting now that we alter these operations max min by taking off maximum over lambda greater than equals to 0 of the minimum over the feasible set of the Lagrangian function, and check that if this max min problem is easier to solve, then you just go for solving it. And now question before us, by solving this problem, can we always expect that we will get a solution of this min-max problem? So question here whether these min-max and max-min problems are having identical solution. It is not always that this max-min and min-max problem will be having identical values, but under certain mild conditions that this set capital F is compact, and here instead of taking this entire set lambda greater than equals to 0, you take a compact set, compact subset of this entire region. So if I take here some set that is compact, here also I take the set capital F compact, and if I pre-assume the function that is coming up over here is convex for every fixed value of x and concave for every fixed values of lambda and mu, then we can show that these min-max and max-min problem are having identical solutions. Given this result, having these min-max and max-min problems are having identical solutions, it is really tempting that you go for solving this max-min problem to solve this min-max problem. Now here you notice that this problem is the Lagrange dual problem that we have formulated. Maximum over lambda greater than equals to 0 of the function theta. So this is how one could have discovered the Lagrange dual problem. This is your min-max perspective to formulate the Lagrange dual problem for the given primal problem. Now I would like to inform you the penalty perspective of the formulation of the Lagrange dual problem. Perspective 2, which is your penalty perspective, where the penalty perspective is as follows. For the penalty perspective to be described, let me just consider the primal problem to be recasted as the problem with just only inequality constraints, because you notice that any equality constraint Hjx is equal to 0 can be equivalently posed as Hjx less than equal to 0 and minus Hjx is less than equal to 0, right? Due to this reformulation of Hjx is equal to 0, we can recast the primal problem only with inequality constraints, and let us not write the equality constraints over here. Will mean that inside these inequality constraints, the equality constraints are hidden. So I'm just going to take up I is equal to 1 to m, then m plus 1 till L many constants. So till m, then m plus 1 till m plus L. Now this inequality constraint problem, with here we have x belonging to capital X. We go for looking at this problem in terms of a penalty perspective, that associated to the constraint function gi, we impose a penalty, say lambda I greater than 0, for the violation of the constraint gix less than equal to 0. That is, if you observe that at a given point x naught in capital X, the gix naught value is greater than 0, then we penalize the objective function by an amount lambda I times gix naught. So if we go for this parallelization strategy, then we notice that no point x in capital X is going to violate any of the constraints, because whensoever a constraint is violated by a point x naught belonging to capital X, then we notice that we are going to impose a penalty of this much amount, and this much amount is being added in the objective function. Once this penalization is imposed in the objective function, then obviously no point would like to violate any of the constraints, and you will be inside the constraint set, right? So I just go for recasting this primal problem as follows, that I formulate the penalty problem for this primal problem as minimization over x belonging to capital X of the function f(x) plus summation of all these penalty amounts, that summation over lambda I gix for I is equal to 1 to all these constants 1 to till m plus l. And here we notice that whenever a point is violating, a point x naught in capital X is violating one of the constraints, then obviously some positive amount is contributed over here, and that will then refrain us to realize the minimum most value, the minimization of the objective function f. The real function that we wanted to minimize is this function. Now I am going to impose all these penalties to refrain you not to violate any of the constraints. If you are violating, a penalty is being added, and then that will frighten you not to violate any of the constraints, right? So that will keep you inside the feasible region of this problem. So this is just a penalty perspective, a penalty formulation of this primal problem. And here question arises, what could be best choices for the values of these penalties, lambda i's? Now here, as we wish to solve the primal problem, the best choices of lambda I, these penalty values, are those possible values which give the maximum most value of the penalty problem, because the maximum most value of this penalty problem will refrain us to move out of the feasible region. If I give a very big amount of these penalties, then obviously it will frighten you not to violate any of the constraints. So to find a minimum point of this function f inside this feasible region, we go for maximizing this problem, that go for taking the maximum most value of this penalty function. If you take the maximum most value of this penalization, then obviously at the end of the day you are frightening of the decision maker not to violate any of the constraints, and thereby making the minimization of this function f over the set of all points in capital X which are satisfying the constraint set, for which then this contribution of this much expression is going to be equals to 0, right? And hence to solve the primal problem we formulate this problem, that maximization of this penalty function, that fx plus summation over lambda I gix. And here I reiterate that when I go for taking the maximum most value of these penalties, then certainly, as you don't like to be penalized, the maximum most value of this problem is going to be given by a particular point in capital X which satisfies all the constraints, for which then we don't have any penalty, and this term is going to be equals to 0. You notice that only when X is belonging to the feasible set, right? And essentially then you are just solving minimization not on capital X but on capital F for the function f, by taking this maximum most of this penalty amount, right? And here we see that this problem is nothing but your the formulated Lagrange dual problem, right? And you know this penalty formulation is actually obtained from the unconstrained formulation of a constraint optimization problem. We notice that a constraint optimization problem, minimization over a set, let's suppose capital F, of the function f, these constraint problem can equivalently be posed as an unconstrained optimization problem as minimization of fx plus the indicator function of the constraint set, where this indicator function is defined by ifx is equal to positive infinity when x is not in capital F and 0 when x is belonging to capital F. So you are just considering that I will penalize you an infinite amount if you are violating my constraints. Then obviously minimization of these function fx plus ifx took place only when small x is belonging to capital F, right? So these equivalents essentially gave us this idea of penalty formulation of the primal problem. We notice that this indicator function is a discontinuous function, and here we have taken up an approximation, a continuous approximation of the indicator function if, that you have taken a linear approximation, a crude linear approximation of this if given by this expression summation of lambda I times gix. Now next I would like to inform you the third perspective, that is the two-person zero-sum game perspective. This perspective is as follows. Through this two-person zero-sum game perspective, one can discover that for every maximization problem, there is a hidden minimization problem. And that is what precisely we have done in the formulation of the dual problem. In the dual problem, we notice that the primal problem is a minimization problem, and in the dual problem, we have constructed a maximization problem. And this maximization perspective of a minimization problem is commonly identified from the two-person zero-sum game perspective. It is as follows: that to grasp the matter of two-person zero-sum game, let me just consider a quick formulation of a two-person zero-sum game. In a two-person zero-sum game, we have two players, say player 1 and player 2, and for both the players we have some strategy sets. Let's suppose capital X and capital Y, and suppose in the game the payoff function is the function fxy. The value of the payoff function for this game is determined in the following manner: that if the player 1 chooses the strategy small x inside his strategy set capital X, and if the player 2 chooses the strategy say small y inside his strategy set capital Y, then player 1 has to pay an amount of fxy to the player 2. You might ask here why player 1 has to pay. Here we notice that we have not restricted the values of fxy. If fxy is negative, then obviously player 2 is paying an amount of fxy to the player 1. So in this manner, it is not always the case that player 1 is paying to player 2 for every actions, right? So here we consider this payoff function fxy given by the chosen strategies small x and small y respectively by the players player 1 and player 2. Here in a game formulation we assume that the players are equally intelligent and both players have full knowledge of the other player's action. That means player 1 knows the strategy set of the player 2 and player 2 knows the strategy set of the player capital X, and we also pre-assume that they are equally intelligent. So given this circumstance, given this formulation of the game problem, what strategies are best for the players player 1 and player 2? What strategies will be chosen by player 1 and player 2? Let us look at this problem from the perspective of player 1, and then later we'll look at from the perspective of player 2. Accordingly, we will try to figure out what strategies will be best and will be chosen by the players player 1 and player 2. From the perspective of player 1, we see that the analysis is as follows. For choosing a strategy, player 1 will analyze in the following manner. that if player 1 chooses a strategy X dash, then we notice that for the chosen strategy X dash of the player 1, as player 2 is equally intelligent, then obviously player 2 will choose that particular strategy, say Y dash, for which this f X dash Y dash is the maximum most value of f X dash Y, is not it? Because player 2 always wants maximum most amount as much as possible to be dragged out from the player 1, right? So for the chosen X dash of player 1, obviously player 2 will choose that particular strategy Y dash, which gives the maximum most value of this f X dash Y. So by varying this X dash, player 1 will then form a function that is the function maximum over the set capital Y for all possible values of x's, which we note that is a function of x. Let's suppose phi x. So for each and every small x in the strategy set capital X, player 1 will figure out this value phi x, and player 1 will choose that particular value of x for which phi x is the minimum most value, right? And that will give the minimum most loss of player 1. And as player 1 needs minimum most loss, that player 1 does not want to give an amount more than the minimum most possible value of this payoff to the player 2. So player 1 will go for choosing that particular strategy for which the minimum most value of this phi x is realized. So from the viewpoint of player 1, this problem will be solved by solving minimization over capital X of the function phi, which is maximum of the function, the payoff function fxy over capital Y. So from the viewpoint of player 1, this game problem is this min-max problem. Now let us look at the game problem from the player 2's perspective. From player 2's viewpoint, the analysis will be as follows. That as player 2 wants as much as possible to be taken out from player 1, so what he will do, he will analyze in the following manner, that if player 2 goes for choosing a particular strategy, let's suppose y bar, then as player 1 is equally intelligent, then what player 1 will choose is that that particular x bar for which if x bar y bar gives the minimum most value of the function fx y bar, where x is belonging to capital X, right? So for the chosen y bar, the strategy of player 2, player 1 will certainly choose that particular x bar which gives the minimum most value of this payoff function, because player 1 wants as less as he can give to the player 2, right? And therefore player 2 will then go for identifying the function psi y given by the minimum most value over the set capital X of the function fxy. Then we'll go for choosing that particular strategy y for which this psi y gets the maximum most value, because player 2 wants as much as possible can be taken out from the player 1. So from the viewpoint of player 2, we notice that the player 2 will be solving this max min problem, to identify the best possible strategy to be chosen in the game, right? So from the player 2's viewpoint, we notice that the game problem is a maximization problem, maximization of the function psi y, and here for player 1 it is a minimization problem, minimization of the function phi x, right? So the same game from the perspective of player 1 and from the perspective of player 2, we notice that once it is a minimization problem and in another
it is a maximization problem. And therefore, for a given minimization problem, there is a hidden maximization problem. And for a constrained optimization problem, this payoff function is given by the Lagrangian function Lx lambda y. As we have seen in the perspective 1, that the primal problem can be recasted as the min-max problem of this function, this Lagrangian function. So the hidden maximization problem is then max min of this Lagrangian function. So for a given primal problem, we can go for solving the max min problem, where this payoff function is replaced by the Lagrange function, and you may aim for solving this problem to obtain a solution to the primal problem. And we notice that this max min problem, maximum over lambda greater than equals to 0, and here this minimum over the set capital X, this problem is nothing but the dual problem, right? So from the analysis of 2% zero sum game, as we have seen that for a given minimization problem, there is a hidden maximization problem from the perspective of player 2. We can aim for solving the primal problem by solving the perspective of player 2, which is the dual problem. For the player 1, the problem is this primal problem. For the player 2, this problem is the dual problem. So this is how one could have discovered the Lagrange dual formulation of the primal problem. Now in the next, then we go for identifying several results on this Lagrange dual problem. But before that, let me mention also here that in the literature of optimization theory, there are several other kinds of duality theories. Those are as follows. The first is this Lagrange dual. Another duals are Dorn dual, Wolf dual, and Monday-Ware type dual. This Dorn dual is possibly the first extension of the duality for linear programming problems to quadratic programming, and it was given by the mathematician Dorn, and hence the duality is named after him, that Dorn's duality. And this Dorn duality is exclusively for quadratic programming problem, not for general nonlinear programming problems. For the first reference of this Dorn duality, you may please visit the article by W.S. Dorn entitled Duality in Quadratic Programming, which came out from Quarterly of Applied Mathematics in the year of 1960. You please look at the volume number 18 in the issue number 2, in between the pages 155 to 162. You will find a detailed discussion of Dorn's duality. This is the pioneering article for Dorn's duality. Wolf duality is the extension of duality theory for linear programming to convex programming problems, and it was done by Wolf, and hence the name Wolf duality. For a fast reference of this Wolf duality, you please look at the article by P. Wolf entitled A Duality Theory for Nonlinear Programming, which also came out from Quarterly Applied Mathematics in the year of 1961, in the volume number 19, in between the pages 239 to 244. This Mondwairs type duality, relaxing the convexity assumption in the Wolf duality, and for a first reference of this Mondwairs types duality, you please look at the article by B. Mond entitled Mondwairs duality, which is essentially a chapter of an edited book, the chapter 8 of the edited book by C. Pierce
and he hunt entitled Optimization, which came out from the Springer publication in the year of 2009. In this book, you please look at the chapter 8. There you will find a detailed discussion on the Mond-wire types duality. And for this Lagrange duality, the mostly used duality theory for nonlinear programming problem is this Lagrange duality, which was pioneered by John von Neumann, a giant in optimization theory. And you know, the popularity of Lagrange duality came out when Neumann conjectured that 2% zero-sum matrix game is equivalent to a linear programming problem. Due to this conjecture of Neumann, which was later proved by Albert W. Tucker, due to this conjecture of von Neumann, possibly Lagrange duality gained the attraction of optimizers, the giants of optimization theories, and hence gained the popularity even in the nonlinear programming problems. Now let me move on discussing a few results on this Lagrange duality theory. The first result on this Lagrange duality is on the convexity of the negative of the dual objective function. In order to drag your attention in between this lecture, you notice that I have mentioned that the dual problem is a convex optimization problem, but the dual problem is actually maximization of a concave function, and hence it can be recasted as minimization of the negative of the objective function, and thereby getting a convex optimization problem. So here at first we shall prove that the dual function is a concave function. Here by dual function I mean the objective function of the Lagrange dual problem. The result one neatly states the following, that consider the primal problem, the problem capital P. Throughout the rest of the discussion, the primal problem will be the general problem, that minimization of fx subject to m many inequalities, gix less than equal to 0, I is from 1 to till m, and hjx is equal to 0 for j is equal to 1 to till l and small x belonging to capital X. And while referring the dual of this problem, we will consider dual with respect to this set capital X. So this is our standing assumption on the problem P. The problem is this one, and on the dual problem, we take the dual of this primal problem with respect to the set capital X. We are not going to alter this set capital X. Otherwise, the dual of this problem will get deferred, right? And therefore, we consider the primal problem P, and then in this result, we assume that let the set capital X be a non-empty compact set in Rn, and also assume that the functions f, all gis and all hj's are continuous functions in the set capital X for all I and for all j. Then the function that is the objective function of the dual problem, your theta lambda mu, which is defined by, if we recall, infimum of the Lagrangian Lx lambda mu over x belonging to capital X. This function theta lambda mu, or in order to be more erudite, we don't write this lambda mu because theta lambda mu is a value, right? Theta lambda mu is not a function. This function theta of the dual problem is a concave function on the set Rm cross Rl. Let us go for proving this result. To prove that the function theta is concave,
Let us pick up a pair of points from this set Rm cross Rl and take a convex combination of those 2 points, and then go for checking out the inequality for concavity of the function theta. For this, let us take a pair of points, say lambda dash mu dash and lambda double dash mu double dash from the set Rm plus L, and also take some number t in between 0 and 1. We then notice that the expression of the function theta at the convex combination of these 2 points t times lambda dash mu dash plus 1 minus t times lambda double dash mu double dash by the very definition of the expression for theta is given by infimum over x belonging to capital X of the Lagrangian at the point x t times lambda dash mu dash plus 1 minus t times lambda double dash mu double dash, which explicitly is that infimum over x belonging to capital X. The expression of capital L is given by fx plus t lambda dash plus 1 minus t into lambda double dash. This expression transpose the vector valued function g plus the vector valued function h times the vector t times mu dash plus 1 minus t times mu double dash, which can be written as, you just cross check that t times fx plus lambda dash transpose gx plus mu dash transpose hx, this expression plus 1 minus t times fx plus lambda double dash transpose gx plus mu double dash transpose hx. This is the expression of the function L at this point. Here in the expression of f, we have just written t times fx plus 1 minus t times fx. Here you notice that this infimum can be thought of infimum on this expression plus this expression, and we know this inequality that infimum of the addition of 2 sets A and B is greater than equals to addition of the individual infimum of A plus infimum of B. From this inequality of infimum, we see that we can write here as infimum over x belonging to capital X of the expression tfx plus lambda dash transpose gx plus mu dash transpose hx, this expression plus infimum over x belonging to capital X of the expression 1 minus t times fx plus lambda double dash transpose gx plus mu double dash transpose hx, right? Here, sorry, we have here t being multiplied over the entire expression. Now here, as the infimum is taken over this variable x, so this t can be brought out of this infimum, and accordingly we can write it as t times infimum of the expression that fx plus this entire expression till mu dash transpose hx, which is simply the expression theta lambda dash mu dash. Similarly here, for this term we will have 1 minus t times theta lambda double dash mu double dash, and therefore we see that theta of the convex combination of these 2 points is greater than equals to this expression, and therefore the function theta is a concave function. This completes the proof of concavity of the function theta, the dual objective function, on the set Rm cross Rl. Now from this result that theta, the objective function of the dual, is concave, we remark here that the dual problem, which is your maximization of the function theta lambda mu over lambda greater than equals to 0, this problem can be equivalently posed as minimization of this minus theta lambda mu over lambda greater than equals to 0, and therefore we see that this problem is a minimization of a convex function over affine constraint set, and therefore the dual problem is a convex optimization problem. And the dual problem is convex optimization problem for any given primal problem, irrespective of whether or not the primal problem is a convex optimization problem. The dual problem is going to be a convex optimization problem. This is really attractive, right? So we can just go for solving this convex optimization problem if it is easy to identify a solution for this convex optimization problem. But even though the dual problem is convex, and it might seem attractive to solve the dual problem and thereby solve the primal problem, we can have a few issues on solving the dual problem. These issues are as follows. The issues are that it is often difficult to find an expression, an explicit expression of this dual objective function, and therefore it will be difficult to find a solution to the dual problem. So I write out here the first issue, that explicit expression of the dual objective function is often difficult to find. And this is due to the fact that the value of theta can be evaluated at a point only after solving a minimization problem. That you look at the expression of theta, you will find that the expression of theta is given by minimization of the Lagrangian function at each and every point lambda mu. You need to find a solution of this minimization of the Lagrangian function Lx lambda mu to find the value of theta lambda mu, and therefore as to execute the value of theta even at a given point lambda mu, we need to solve a minimization problem. It is really tedious and very difficult to find a closed form expression or an explicit expression of the dual objective function. And often an explicit expression for theta in terms of lambda mu is not available. We will have certain example just after writing out all this issue. So let me write out the second issue, that the dual objective function may not be differentiable even if the primal problem is a smooth optimization problem. That means even if the objective function and the constant functions of the primal problem are continuously differentiable, the objective function in the dual theta lambda mu might not be differentiable. And in finding an optimum point for a non-differentiable objective function is a difficult task, and therefore identification of an optimum point or identification of a solution to the dual problem is not an easy task. So I write out here that the dual objective function may not be differentiable if the primal problem is a smooth optimization problem. The third issue is a bit strange, that the dual problem may not have a solution even if the primal problem has one. And conversely also the same is true. The primal problem may not have a solution even if the dual problem has one. So I write out here the issue that the dual problem may not have a solution. Whereby this may not have a solution, I mean may not have an optimum solution. Let me now include one example each for one of these three issues. The first example, I will show that dual does not have an explicit expression. Towards this, the example that I would like to take up is the following problem, that you consider the set capital X is Rn, and in the primal problem formulation you consider a few matrices A, B, C and D. Those are matrices of orders. Capital A is of order m by n. Small b is an m vector. Capital C is of dimension say p by n, and D is a p vector. Now consider the primal problem as the problem minimization of the difference of ax minus b. Its Liebig one norm subject to the constraints that Cx is equal to. Then for this primal problem P, the dual problem is given by the maximization of theta mu, where mu is belonging to, we have P many constraints here, so mu belonging to R, where we notice that the expression of theta lambda, which is given by infimum over x belonging to capital X, which is Rn here, of fx, which is ax minus b Liebig one norm, plus mu transpose cx minus d. But to find the value of theta lambda for a given lambda, which is given by this minimization of this expression, which can be recasted as a linear programming problem. So just to find a value of theta lambda for a given lambda, we need to solve a linear programming problem. And for this objective function theta lambda, there is no explicit expression. Now next I will give an example where the objective function of the dual may not be a differentiable function even if the primal problem is a smooth optimization problem. But before that, let me just give you a home task here, as I have considered here a problem where the constraint is given by only linear equalities. Let me consider a linear programming problem and ask you to find the dual of this linear programming problem. Find the Lagrange dual, that is the dual that I have formulated so far, the Lagrangian dual problem of the linear programming problem, where in the linear programming problem we go for maximizing say C transpose X subject to Ax less than equal to B, X greater than equals to zeros, and here I am taking X is belonging to Rn. C is a vector in the n-dimensional Euclidean space, so C is in Rn, a given constant vector. The matrix capital A is a matrix of order m by n, and B is an m vector. B has m many components. So here we have m many inequalities together with here also n many inequalities. Subject to these two constraints, you go for maximizing this linear function, and thereby you are considering a linear programming problem. Now go for finding the Lagrange dual problem of this linear programming problem. I am keeping this as a home task. Now let me go for the next example. I am going to give an example of non-smooth dual objective function. Towards such an example, consider this primal problem and take the set capital X to be the set of all points x1 x2 in R2 such that x1 is lying in between 0 and 1 and x2 is lying in between 0 and 2. You take these as your set capital X and consider this primal problem. Then with respect to this set capital X, let us now go for finding the dual problem of this primal problem. To find the dual problem, at first let us consider the Lagrange function, the Lagrangian function for this primal problem with respect to this set capital X. The Lagrangian function is given by Lx. You have only one constraint left over, so Lx lambda, where x has two components, x1 and x2. So this expression is given by minus x1 minus x2 plus lambda times g1x, that is your 2x1 plus 4x2 minus 3. So the dual objective function is given by the theta lambda, which is equal to infimum over x1 x2 belonging to capital X of the function Lx1 x2 lambda, right? So explicitly this is equal to infimum over x1 lying in between 0 and 1, x2 lying in between 0 and 2 of the expression that here we will get minus 3 lambda plus the coefficients of x1 are minus 1 here and plus 2 lambda plus x2 times the coefficient of x2 is minus 1 plus 4 lambda, right? And therefore this expression can be written as minus 3 lambda can be brought out of this infimum because minus 3 lambda is not dependent on x1 and x2 plus infimum over here, as in this expression we only have x1, so this set will now reduce for this term as only on x1 in between 0 and 1 of the expression x1 times minus 1 plus 2 lambda plus infimum over x2 in between 0 and 2 of the expression x2 times 4 lambda minus 1. Now let us go for executing this expression. At first let me separately identify this expression and then this expression. To find this expression, we notice that if this term 2 lambda minus 1 is non-negative, then we notice that this infimum value is given by the value 0, right? But if this 2 lambda minus 1 is negative, then this infimum value is given by at the point x1 is equal to 1. So we get this expression as 0 if 2 lambda minus 1 is greater than or equals to 0, and it is your 2 lambda minus 1 if 2 lambda minus 1 is negative. Similarly here you will find that the value is equal to 0 when 4 lambda minus 1 is greater than or equals to 0, and when this 4 lambda minus 1 is negative, then in that case you will have this expression given by 2 times 4 lambda minus 1, and therefore these two terms together we notice that will give us, in terms of breaking values of lambdas, here we need to give a breaking at lambda is equal to half, here at lambda equals to 1/4. So we consider a breaking of the lambda values broken at 0, then at half, at 1/4. If we consider lambda in between 0 and 1/4, then we see that this expression is given by this 2 lambda minus 1 and this expression will contribute here 2 times 4 lambda minus 1 when lambda is in between 2 till 1/4. Now in between 1/4 to half, this expression will give us 0, but this expression will now give us 2 lambda minus 1. So for lambda greater than equals to 1/4 till half, we have this is your expression contributed by this and this term. And when lambda is greater than equals to half, then we notice that both these and these terms, they are contributing us 0 values. And therefore ultimately the expression of theta lambda for lambda in between 0 and 1/4 is given by this minus 3 lambda plus this entire expression, which gives us 7 lambda minus 3. When the value of lambda is in between 1/4 to half, then the expression of theta lambda is given by minus 3 lambda plus this expression 2 lambda minus 1. And when your lambda is greater than equals to half, we have the expression of theta lambda is given by 3 lambda. So this is your entire expression of the objective function theta lambda. Now here I would like to give you a home task that you find the graph of this function theta lambda, and you figure out that this theta lambda is a continuous function, but it has non-differentiability at the points 1/4 and half. So this function has exactly 2 points at which the function theta is not differentiable, but it is a continuous function. So here we have gotten one example where for the primal problem was a problem of minimizing a linear function subject to linear constraints. We see that the dual problem is having the objective function non-smooth. Now I would like to give an example in which we will find that although the primal problem is having an optimum solution, but the dual does not have any optimum solution. Towards this, we consider the following example, that consider the set capital X to be the real number set and the primal problem as the problem which is minimization of the function say x plus 2010 subject to the constraint that half x square is less than equal to 0 and x is belonging to capital X. Note here that this primal problem is having an optimum solution because trivially the point x is equal to 0 is an optimum solution. But for this problem P, the dual problem has the objective function given by the following calculation, that the Lagrange function for this problem P is given by Lx lambda, which is equal to your x plus 2010 plus lambda times half of x square, right? And therefore the dual objective function, or casually the dual function, is given by theta lambda is equal to infimum over x belonging to capital X, which is capital R, of this function Lx lambda, which simply can be observed as, you please figure out that this is your 2010 minus 1 over 2 lambda. You please figure out why. And therefore the dual problem is your maximization of this function theta lambda over lambda greater than equals to 0, which is your maximization of this 2010 minus 1 over 2 lambda subject to lambda greater than equals to 0 we notice that this function does not have any maximum over lambda greater than equals to 0, right? And therefore the dual problem does not have any optimum solution, even though the primal problem is having an optimum solution. Now next I would also like to give an example where the dual has an optimum solution but the primal does not have one. For such an example, I will give the example as a home task. You please figure out that consider the problem minimization of e to the power minus x subject to x greater than equals to 0, and you take x belonging to capital X where capital X is the set capital R. You consider this problem and so that the dual problem for this primal problem is having a solution, is having an optimum solution, but this primal problem is not having an optimum solution. This is very trivial. For this primal problem, we all know that if I just go for graphing it out, the objective function for x greater than equals to 0, then we see that e to the power minus x has graph like this one. The x-axis is an asymptote to the graph of y equals to e to the power minus x, but this function y is equal to e to the power minus x does not have any minimum point, and therefore this primal problem does not have an optimum solution. But you go for constructing the dual of this problem, you will realize that the dual problem is having an optimum solution. Now next we shall explore the relationship between the primal and the dual optimum solutions if they exist. Towards this, the first result is the weak duality theorem, which states that for any given primal and dual feasible points, the dual objective function value is lesser than equals to the primal objective function value. So neatly we state here the weak duality theorem, which states that let x naught be a feasible point to the primal problem, and let's suppose lambda dash mu dash is a feasible point of the dual problem, then the dual objective function value at lambda dash mu dash is less than equal to the objective function value of the primal at the point x naught. The proof of this result is really straightforward. The proof is as follows, that by the definition of theta lambda mu, we notice that theta lambda dash mu dash is given by infimum over x belonging to capital X of the expression Lx lambda dash mu dash, right? And this is identical to infimum over capital X of the expression of capital L, that is your fx plus lambda dash transpose gx plus mu dash transpose hx. Now this infimum of this entire expression is certainly less than equal to the value of this function at a particular point in capital X. Now as the point x naught is given to be a point that is feasible to the primal problem, therefore x naught is belonging to capital X. So we can write this, that this infimum of this entire expression is less than equal to if x naught plus lambda dash transpose gx naught plus mu dash transpose hx naught. But we notice that x naught is given to be a primal feasible point, right? And therefore this hx naught has all components 0, and all components of gx naught are less than equal to 0. And here, as this lambda dash mu dash is a dual feasible point, we have lambda dash has all components greater than equals to 0. So these two terms together once multiplied component wise, we will have this entire term is less than equal to 0, right? And therefore we get here that this entire expression is less than equal to fx naught, and that is what your result. The value of the objective function of the dual at a feasible point lambda dash mu dash is less than equal to the objective function value of the primal at a feasible point x naught. And as this relationship is happen to be true for every pair of feasible points lambda dash mu dash and x naught, we see that the dual objective function value is always lesser than equals to the primal objective function value, and thus this result is known as the weak duality result. The dual objective function value is weaker than the primal objective function value. Now from this weak duality result, we have a few immediate corollaries. At first, before getting into the corollaries, let me mention you here that as the dual objective function value is always weaker than the primal objective function value, that is, as this relationship is true, so this relationship eventually gives us, if I go for taking maximum over lambda greater than equals to 0 of this function theta lambda mu, if the maximum value exists at all, then we notice that this maximum value is certainly less than equals to fx for any feasible point x to the primal, right? And therefore, as this is a constant value, this maximum of this theta lambda mu is a constant value, fx is greater than equals to this constant for every feasible point x. So the minimum most value of this function fx over this feasible set is certainly bigger than equals to this constant value maximum of theta lambda mu. So ultimately we get that minimum over capital F for the function f is greater than equals to maximum over lambda greater than equals to 0 of the dual objective function theta lambda mu. If these two optimum values, the optimum value of the primal and the optimum value of the dual, if they are equal, then we call strong duality is realized. But it is not always the case that for any given primal problem you have the maximum value of the dual is equal to the minimum most value of the primal. If they are not equal, then the difference of the minimum most value of the primal and the maximum most value of the dual, this difference is named as the duality gap, which is the difference between the optimum value of the primal and the optimum value of the dual. If this duality gap is equal to 0, then we say that the strong duality holds. And otherwise, that is when duality gap is greater than 0, then in that case we see that a weak duality, this result is happening to be true. So as a note, I write out here that if there exist optimum values or optimum solutions to both primal and dual, then we see that this is happening to be true, that the maximum most value of the dual is less than equal to the minimum most value of the primal. Now next, let me give an example where we will realize that duality gap can be positive for some examples. Towards this, let me consider the following example, that take a set capital X to be the closed and bounded interval 0 to 1, and the primal problem P as maximization of x square, which is minimization of minus x square, subject to x less than equal to half and small x belonging to capital X. Consider this problem, and for this problem certainly you can easily find that the primal optimum solution is obtained at the point x is equal to half, where fx is this expression minus x square, and therefore it is equal to minus 1 by 4. But what about the dual? To find the dual of this problem, let us at first identify the Lagrangian function, which is given by Lx lambda is equal to minus x square plus lambda times 2x minus 1, and therefore the dual function, the objective function to the dual problem, is given by theta lambda, which is infimum over x belonging to capital X, that is the interval 0 to 1 of this expression Lx lambda, which you just find with an analysis with this term. You will find that this expression is minus lambda for lambda greater than or equals to half, and when lambda is less than half, we have this expression of theta lambda given by lambda minus 1, and hence the maximum most value of theta lambda is equal to, you just figure out that at the point half the maximum most value is attained, and at the point half you have the value is equal to minus half. So we see that the primal optimum value is minus 1 by 4, the dual optimum value is minus half, and hence there is a duality gap, which is given by the difference between these two values, that is your minus 1 by 4 minus half, which is equal to 1 by 4, a positive quantity. Let me now also mention an example where there is no duality gap. For such an example, you consider the primal problem as the minimization of the function x1 square plus x2 square subject to x1 plus x2 greater than or equals to 6, and you take out x is belonging to the set capital X, where capital X you consider the first quadrant of the R2 plane. For this problem, you can easily figure out what is the optimum solution. Just geometrically you draw out the feasible region, you will find that optimum solution to this problem is attained at the point 3 3, and hence the optimum solution, the minimum value of this objective function in the constraint set, is equal to 18. And for this problem you go for formulating the dual problem, and let me hint out here, the dual objective function will have the expression theta lambda is equal to a smooth expression given by 6 lambda minus lambda square by 2, which is a smooth function, a differential function. So you have gotten an example here that the dual objective function can be a smooth objective function. Now for this problem, you please show that there is no duality gap. You will find that at the optimum solutions for both the primal and the dual, the values are same, the value 18. Now we will consider a few immediate corollaries to the weak duality result. The first corollary towards this is the following, that if you have found a pair of feasible solutions to the primal and the dual, at which the value of the primal objective function and the value of the dual objective function, they are same, then these pair of feasible points x star and lambda star mu star, they are certainly optimum points, a minimum point of this primal problem and a maximum point of this objective function theta of the dual problem. So if
This equality is realized for some primal and dual feasible points x star and lambda star mu star respectively, then x star is an optimum solution to the primal and lambda star mu star is an optimum solution to the dual. A proof of this result is straightforward, and coming out from the weak duality result, we notice the following. From the weak duality result, we have seen that for any feasible point x to the primal and a feasible point say lambda mu to the dual, we have theta lambda mu less than equals to fx, and from here we have seen earlier that maximum over lambda greater than equals to 0 of theta lambda mu is less than equal to minimum over x belonging to the feasible set of the function f, and hence we notice that as x star is a feasible point to the primal, so this minimum most value of this function f over the feasible set capital F, we have this minimum most value is less than equal to fx star. Similarly, as lambda star mu star is a feasible point to the dual, we have the maximum most value of theta lambda mu over the feasible set is bigger than equals to theta lambda star mu star. Fine. Now from the hypothesis that fx star is equal to theta lambda star mu star, we have this quantity is equal to this quantity, and hence inside of this inequality all the four quantities are equal, and so we have fx star is equal to the minimum most value of the function f over the feasible set capital F, and theta lambda star mu star is equal to the maximum most value of theta lambda mu over the feasible set of the dual problem. And hence that proves the result that this pair of points x star and lambda star mu star are optimum solution to the primal and to the dual respectively. Now as a next corollary, I would like to inform you that if the dual problem is unbounded, by that I mean if the supremum value of the objective function of the dual in the feasible set of the dual is positive infinity, then we can show that the primal problem has no feasible solution, no feasible point. The feasible set is empty. Because if the primal has a feasible point, then we see that if I consider, let's suppose x naught is a feasible point to the primal, then we see that for any feasible point to the dual, we have theta lambda mu is less than equal to fx naught, and therefore whatsoever lambda mu you are going to choose, you choose, but lambda mu value cannot exceed this upper bound fx naught, and hence if there is a feasible point to the primal, the dual objective function cannot be unbounded above, and therefore if the dual objective function is unbounded above, then the primal problem cannot have a feasible point. Now here let me mention a very interesting fact that can be extracted from all this analysis of weak duality results, that you see that with the help of the weak duality results we can find a measure of goodness of an approximate solution, say x hat, to the primal problem. This can be done as follows. Let's suppose we need to solve a constraint optimization problem, say minimization of a function f over the set
capital F. And by some optimization method or optimization algorithm to solve this problem, let's suppose we have arrived at an iterative point, let's suppose x hat. This x hat is a feasible point, and reaching at this iterative point x hat, a question comes that can we measure how far we are from the minimum value of this objective function. Let's suppose the minimum value is equal to say f star, and to measure a goodness of how far we are from this f star at the current iterate x hat, what we can do is the following analysis. You can feel that I will just go for finding out the difference between f x hat and f star, and then I will find a measure of how far we are from f star. But we notice that before solving this entire problem, we do not know what is the value of this f star, right? So a measure of how far we are from the optimum solution to the primal problem cannot be identified by measuring out this difference. But surprisingly, this weak duality result can give us a way to check the closeness of x hat to an optimum point through the following way. The way is the following. Suppose that during the course of an optimization algorithm, we have a candidate primal feasible point x hat and a dual feasible point, let's suppose lambda hat and mu hat, such that the difference between this objective function value of the primal at x hat and the dual objective function value at a lambda hat mu hat is lesser than certain epsilon. That is, let's suppose if x hat minus theta lambda hat mu hat is less than a small quantity, say epsilon. Then from the weak duality result, we see that the value of theta at lambda hat mu hat is less than equal to the maximum most value of theta lambda mu over lambda greater than equals to 0, which is further less than equal to the minimum most value of the objective function of the primal in the feasible set, and that we have denoted by f star. We have just denoted, we do not know what is the value of this f star, and this is further less than equal to f at x hat. Now if the difference between f x hat and theta lambda hat mu hat is less than epsilon, we see that the difference between these two quantities, that f x hat and f star, is certainly less than epsilon, right? Because if the difference between this quantity and the rightmost quantity is less than epsilon, therefore difference between any of the two quantities out of these four is less than epsilon, and hence certainly this inequality is happening to be true. So you devise an optimization algorithm in which we execute both primal and dual iterative points. Then we see that if at the kth iterate primal and the dual variable values are all these xk, lambda k, mu k, then go for checking the difference between f xk and theta lambda k mu k. If this is less than epsilon, then you are sure that you are just epsilon distance away from the exact minimizer of the primal problem. And this is really fascinating, that without knowing the value of this f star, without knowing this, just by knowing that what is the difference of the primal and the dual objective function value, you can estimate how far you are from the optimum solution, from the true optimum solution to this problem. So this entire expression, this can be considered as a stopping condition of an optimization algorithm for a constraint optimization problem. And fascinatingly, in one of the most efficient optimization method, the interior point method for convex optimization problem, uses these condition to check out how far we are from the optimum solution at the current identity point xk lambda k mu k. Now next I will go for stating out two particular results on strong duality, that under which conditions we can realize that there is no duality gap of the primal problem and of the dual problem. The first condition towards this is that convex optimization problem together with the Slater's constant qualification implies strong duality. The result neatly states the following, that you consider the primal problem to be a convex optimization problem. That is, we take up the set capital X be a non-empty convex set, and the objective function f and the constant functions all GIs are convex functions, and the functions for the equality constraints, those are affine functions. And also suppose the Slater's constant qualification is holding to be true for the primal problem. That is, we suppose that the following constant qualification holds, that is, your there exists a point x hat in the set capital X such that all the components of G is a vector valued function consisting the components as the G1, G2, G3 and so on, that I have mentioned earlier, that Gx hat is less than 0, all the components of G are strictly less than 0, and Hx bar is equal to 0, all the components of H are is equal to 0 at the point x hat, and together with the condition that the point 0 is an interior point of the image of the vector valued function H of the set capital X. Under this constant qualification, we can show that the strong duality result happens to be true. That is simply the minimum most value, or in terms of mathematical correctness, the infimum most value of fx belonging to capital X, gx less than equal to 0, hx is equal to 0 is less than equal to the supremum most value of the dual objective function for lambda greater than equals to. So in the feasible set of the primal, the infimum most value of the primal objective function value is less than equal to the supremum most value of the objective function of the dual problem for the dual feasible set lambda greater than equals to 0. I will not go for proving this result. For a proof of this result, you may please visit the book by Bazaras Ralisetti on the page number 265, where you will find the theorem 2.6.4, where you will find that this strong duality result is true. Oh, I am very sorry, here it is not less than equal to. This is your equal to. Then only the strong duality can be realized, right? Now, in this theorem 1, we notice that we are mentioning a strong duality result to be happened for a convex optimization problem. But can we go for giving a condition for a general optimization problem, even for a non-convex optimization problem? Towards this, we require a saddle point condition. By saddle point, we mean the following, that a point x bar, lambda bar, mu bar is called a saddle point of the Lagrangian function if the point x bar is belonging to capital X, lambda bar is greater than equals to 0,
and you have the conditions that L x bar lambda mu is less than equal to L x bar lambda bar mu bar, and this is less than equal to L x lambda bar mu bar for all small x belonging to capital X and all lambda mu with lambda greater than equals to 0. We notice that this condition is essentially meaning that the point x bar together with lambda bar mu bar is such a point that x bar lambda bar mu bar is a minimum point of the function Lx lambda mu if we focus our attention only on the values of lambda and mu as lambda bar mu bar. That means for this function Lx lambda mu, where the value of lambda is lambda bar and mu bar, for this function the point x bar is a minimum point that is assumed from this inequality, this side, and from this side of the inequality we notice that this assures that the point lambda bar mu bar is a maximum point of the function Lx bar lambda mu. So as if we are focusing our attention on these two variables and we keep our attention on the fixed values of these lambda and mu, then you are realizing that the point x bar lambda bar mu bar gives the minimum most value of the Lagrangian function when we have fixed our attention on this lambda bar mu bar, and when we fix our attention on x is equals to x bar, then you notice that this Lx lambda mu has maximum most value at this point x bar lambda bar mu bar. So as if we are at this point x bar lambda bar mu bar at which there is a minimum when we fix our attention on this lambda bar mu bar, and there is a maximum when we are fixing our attention on this x is equal to x bar. And thus this point x bar lambda bar mu bar is called a saddle point of the Lagrangian function Lx lambda mu. The next result on strong duality is on existence of a saddle point for a given constraint optimization problem, irrespective of whether or not it is a convex optimization problem. The strong duality result for a general constraint optimization problem is as follows. It states that a point x bar lambda bar mu bar with x bar belonging to capital X and lambda bar greater than equals to 0 is a saddle point for the Lagrangian function if and only if the point x bar and lambda bar mu bar are respectively optimal solution to the primal and dual with no duality gap. So if there exists a saddle point of the Lagrangian function, then for the given primal problem there will be no duality gap and vice versa. A proof of this result can be found from the page number 269 of the Bajras-Ralisetti's book, where you will find the theorem 6.2.5, where a proof of this theorem 2 is given. With this result of strong duality, let me now go for wrapping up this lecture. But before stopping this lecture, let me mention that as we have discussed a bit about the Lagrange duality theory, it is worth reflecting on the possible incentives for solving the dual problem in place of the primal. The incentives for solving the dual problem are as follows: that the very first point, a very attractive point rather, the dual, the Lagrange dual problem is a convex optimization problem. And by now we know that handling convex optimization problems are easier than non-convex optimization problems. So if the primal problem is a non-convex problem, then you go for framing the dual problem and solving it out. And by solving the dual problem, possibly you will get a solution to the primal problem. Even if you have not gotten a solution to the primal problem by solving the dual problem, you have at least reached very close to the primal optimum solution. And thereby, the dual optimum solution will give you an warm start, a warm initial point to start an optimization algorithm to solve a constrained optimization problem. By this warm start, I mean instead of choosing initial point arbitrarily from the feasible set, you go for choosing the initial point to be a point at which the primal objective function value is equal to the dual objective function value. The second point, the second incentive is that the dual problem, you have noticed that the dual problem has simpler constraint. The constraint of the dual problem is just given by lambda greater than equals to 0, right? And not only that, commonly the dual problem has a smaller dimension. The number of variables in the dual problem is commonly smaller than that of the primal problem. And therefore, the dual problem might be easier to handle than the primal problem. So I write out here that the dual problem may have smaller dimension and simpler constraints than primal. And the third incentive is that under certain circumstances, that means under certain assumptions that we have taken in this theorem 1 and theorem 2 in the strong duality result, under those circumstances, when there is no duality gap, then from the solution of the dual, we can find a solution to the primal. And last but not the least, we have seen that the duality theory can give a potential means of termination criterion for optimization algorithm. That at the current iterate xk, you can measure how far you are from the optimum solution of the primal problem. So I write out here that duality theory gives a potential means of termination criterion for optimization algorithms to solve constant optimization problems. With these comments, I now stop this lecture here. In the next lecture, we shall get into a new topic, a new unit of the course, that is optimization algorithms to solve constraint optimization problems. I now put here a sincere thanks for all of your kind attention. Thank you. Thank you all.